Hello friends, welcome to follow up. Let's have a look at problem 222 again. So this problem asks us to find the total number of nodes in a complete binary tree. So in a previous video, we have given a solution based on recursion format. So here we want to have another solution format, which is based on binary search. So actually this problem is marked easy as by leetcode if we do not consider term complexity. But if we want to work out a solution which is better than a linear term complexity solution, so actually it deserves some deeper thought. So here notice that we see linear and the O of n. So n is the total number of nodes, right? So from the previous video, we know that the total number of nodes, if it's n, right? Then at the depth, let's call it d. So here I call the depth is the number of levels. I use this convention. So for example, for this tree in example 1, the depth would be 3 in our current convention. Some textbook, so they use the indexing. For example, the first layer is indexed 0, and the second indexed 1, and the third indexed 2. So this will give us a depth 2, right? So we need to distinguish the two conventions. So with that said, we want to give a solution based on binary search. So actually, if you have followed up for some period of time, you notice that you should have noticed that we have a binary search playlist. So there we have a lot of examples on how to do binary search. So in general, so if we want to do binary search, there are two steps. One is to define a Boolean function to produce order or monotonicity. Another one is to do search range shrinkage. So actually, for the two steps, sometimes it can be tricky. So here I want to use this example to demonstrate to you how to use binary search effectively or with a better understanding. So if you look at this code, this is the solution for previous video. So here I'm going to copy this part. Let's do this. Let's copy this part. Basically, I want to copy the class and the function signature. I'm going to call this one v1. And then let's focus on here. So here, as we have digested that, so for complete binary tree, so the main thing is that we compute the number of nodes in the last layer or last level. So because if we do not include the last level, the tree will be a full tree. Well, for a full tree, it's very easy to compute the number of nodes. For example, here you have a full tree of 3 levels, right? So the number of nodes will be 2 to the power 3 minus 1. So 3 is the total number of levels. So here we use 3, right? So then if we want to get the last layer nodes, so we can do binary search. So that's the main observation. So here, what we want to do is that we need to first know at least the depth. Because for example, if we want to locate this node labeled 6 with value 6 and labeled, let's see, this is 0th node, this is the first node, the second node. Then we need to first go to right, then go to left. Then how do we determine the direction of a movement? So this actually will be incorporated with binary search. So we are going to explain this logic. So for this current solution, first let me write a function to get the depth. So here depth. So we are going to write within this count node function. So if not root, so I'm going to return 0. Otherwise, we are going to return 1 plus depth root left. So notice that this depth is returning the total number of levels. For example, in this example, the return will be 3. So now let's first get this information. So D is depth, the root, right? So if the total number of levels is 3, so we need to move 2 times. For example, if we want to test if another node exists in the tree, for example, let's imagine it has a value 7 and the index as 0, 1, 2, 3, right? So then you should move to right, and then right again. But you know, if we check the right again, so it's null. So it means that we do not have that node. So we only have this one. So this one has an index 2. So this will telling us, oh, in the last layer, we have 3 nodes. So then we use this 3 plus this 3. We're going to get 6, right? That's our overall thought. So now let's use our intuition. Now we have D levels, but we are not sure if the last levels is fully filled. So in this case, we know we have a D-1 level full tree, right? So let's first count those number of nodes. So this will be say 2 to the power, let's see, so D-1, right? -1. So this is the number of nodes in the full tree. So now what we want to do, let's keep this information. We can finally, when we do the return, we count this part. And then we can use binary search to count the number of nodes in the last level. So here, first, we need to define a Boolean function to check if a count is corresponding to a valid node. So for example, if I count 2, it corresponds to a valid node 6. If I count 3, so it does not correspond to a valid node. So in other words, so in the last layer, we have only 3 nodes. So this is actually very intuitive to write. So here, let's see, define can find. I'm going to pass it a value, and then we're going to pass a node or root. So let's write root. Let's write root. It might be better. So here, if I use root, we need to pay attention to the variable scope, right? So here, left and right. So we're going to label it. We imagine the last layer is in full, right? So then the first node will correspond to index 0. And the last node will correspond to the power, because in this tree, the last node is level D-1. So it's D-1. So then this is the total number of nodes. The index will be -1. So then what we want to do, because here we have 3 levels, so we need to travel twice, right? So here we just need to travel, so we have D levels, so we may travel D-1 times, right? So we want to find if this value or index, so this value is corresponding to a valid index, corresponding to a node, valid node, non-null node. So let's do mid. So we can do left plus say right minus left over 2. So in this case, we're going to compare the value. So if it's less than or equal to middle, it means that we need to move to the left, right? For example, if you check this node, it's 1. So we need to, from the root, move to the left. So in this case, the root equals root left, right? So then in this case, also we need to update the right, so it be made, right? Otherwise, the value or the index is very large, so we want to, in other words, it's larger than 1/2. So we're going to move to the right because it's located in the right subtree if existed. So we are going to do root equals root right. And then in this case, we're going to update the left. The left will be made +1 at least, right? So afterwards, we're going to check if after d minus 1 selection, so we want to check if the corresponding node is a valid node. If so, it means that we have at least this number of nodes in the last layer, right? So we want to return node is not null. So this way we finished the Boolean function. Next is binary search and the search range shrinkage. So actually we can easily determine how to do this using especially example 2 and example 3. So here let's first do something like this. If not root, I'm going to return 0. So just treat this edge case. And then we are going to set L and R to be 0 and 2 to the power d minus 1, the minus 1. So this is the first index, and this is the last index if the last layer is in full, right? So now what we want to do is, well, left is less than or equal to R. So later I'm going to explain why we need equality. So you can think of a single node tree. We'll come back to this point, right? So let's compute mid. So we're going to shrink 1/2. So L, R minus L over 2. So in this case, if can finish, so mid root. So in other words, mid corresponds to a valid index. Then in this case, we're going to set L to be mid in general, but here we need to put it to be mid plus 1. We will see, and L, this will make L minus 1 always makes find L minus 1 root is true. So otherwise, so if it is not true, so mid is too large, so we're going to set right to be mid minus 1. So finally, the L will be the corresponding counting, because L here we make it plus 1. So this L minus 1 is the largest valid index, so the counting of node will be L. So this way we need to return 2 to the power and d minus 1. So this part is d minus 1 levels full tree number of nodes, and then we're going to also here minus 1, then we're going to plus L. So before we make any comments, I guess let's first do a test. So we have changed this to be v1. So here let's do it. Can finish is not defined. Let's see. Can find. Node is not defined. So here we see root, right? Because here we're in the root. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes all the cases. So here let's treat this case. So why if we write L less than or equal to R? Actually, this corresponds to example 3. So for example 3, let's see. In example 3, so because we know the level d is 1, right? Then in the last level, we have number node is 2 to the power and d minus 1. Then so this minus 1, 2, this is also a 0. This is the largest index, right? So in this case, we are going to have L equals 0 and R equals 0, right? But because it was one node, we need to enter this while loop. Therefore, we write L less than or equal to R. So if it does not enter this L, so the count of L will be 0, right? but here is also 0, then 0 plus 0 is 0. It's not right. But if we enter this while loop, so we have L and R equals 0. So mid is also 0, right? So after, because this is valid if you use 0, then we set L equals 0 plus 1, that is 1. So later L will be 1, so this total will be correct. So this is one case. So another case we need to pay attention to is here. We didn't write just a mid, right? So here we make L minus 1 always make this binary function true. This is also important detail to notice. So this is 2 points we commented. Let's regarded that as comment 1. That is the 2 remarks here. So the second comment will be term complexity, right? So for term complexity, so we know if we compute the depth, so the term complexity will be O of D. And then if we want to do binary search, so this is the search range, 2 to the power D minus 1 minus 1, roughly 2 to the power D, right? So when we do binary search, the number of shrinkage we done is nothing but logarithm 2 of 2 to the power, roughly 2 to the power D, right? So here is D minus 1, it does not matter. So this will be nothing but D, right? So then this 2 is a relation multiplication, right? So we're going to have O D times O D, right? It's nothing but O D square. So but what's D? As D is roughly so logarithm of total number of nodes, then to the power 2. So in other words, it's O log m times log m, right? So this is a much better term complexity compared to linear. So the reason is that it's very easy to verify. You verify that if you know some calculus. Let's see, calculus. So this will be, we know this limit, so logarithm, so n to any power, right? To any positive power. Let's see, k. Then you divide by n. So this limit will be 0 as n tends to positive infinity. So here k is anything greater than 0, right? So here we have k equals 2, right? So for sure, in mathematical language, this means the solution is sublinear. So with that said, I guess that's about it for this second video for this problem. I would add something extra. So this problem is actually a very classic problem. But if you do it just using traversal and counting, I guess that's not the intention for this problem. Here the main point, I guess, is that we want to have an algorithm runs in less than linear term complexity. So with that said, I guess that's about it for this video. Thank you.